so today we're doing lesson 6.1, which is an intro to systems of equations with two variables. Today we're going to learn two methods of how to solve those systems, so graphing and substitution. Go ahead and pause the video to work out the warm-up on your own, and then you can unpause it to come back and make sure you have the correct answer. Okay, so we have not done an intro yet to systems of equations, but this one here is a little bit easier than the ones that we're going to work with today because it actually already has one of our variables solved for. So we are given this first equation, which tells us that x equals 1, and then we're given the second equation with two variables, both the x and the y. So hopefully what you guys were able to see here is that we can take this x value and substitute it in for the x in the second equation. So that would become 2 times, now 1 instead of x, minus y equals 7. 2 times 1 is just 2. Then we have minus y equals 7 again. So now to isolate y, we would subtract 2 from both sides. We'd get negative y equals 5. And then remember, if you have a negative in front of a variable like this really means I have a negative 1 multiplying out in front, which I can then divide by so that I get y equals negative 5. Okay, so there's my solution. All right, before we fully jump in today, we're going to quickly review y equals mx plus b. This is slope-intercept form, which you guys probably remember from your previous math classes. And then the m here, that is what represents our slope. Sometimes we refer to it in lower classes as our movement. That's kind of a way to connect m to movement. So slope, which is also the vertical change over the horizontal change from one point to the next. So if we look at this example, for instance, we would see, okay, how much do I have to go up and over to get from this point to the next point to the right? So I went up 1, 2, 3, 4 units over 3 units. So my change in the vertical direction, or change in y, was 4, over my change in the horizontal direction, or change in x, was 3, and therefore my slope would be 4/3. Okay, and then b, that represents the beginning spot on the y-axis, or in other words, the y-intercept. This is also where the y value is when x is plugged in to be 0. Okay, so we see that here on this graph at 0, negative 2, and therefore if we were to find the actual equation for this, this would be y equals our slope, 4/3, times x, minus 2, our y-intercept right there. Okay, so the reason we review that is because our first way or first method of solving these systems is going to be via graphing. This is especially helpful if we're dealing with a bunch of fractions, just because graphing a fractional slope can be a little bit easier than solving with it algebraically. So I'm going to go ahead and put stars by these two equations here. You can write them down. You can use different colors on your own notes if you'd like to do so. And then let's start with identifying the y-intercept. So my y-intercept is 0, 1. I'm going to put a point there. And then my slope here, like we just talked about, is 4/5. So I'm going to go up 4, 1, 2, 3, 4, over 5 to the right, 1, 2, 3, 4, 5, and put a point. Then up 1, 2, 3, 4, over 1, 2, 3, 4, 5 again. Or backwards, go down 1, 2, 3, 4, over 1, 2, 3, 4, 5 to the left, and then you can continue going backwards. Okay, then you can plot your line here. And whenever you are actually plotting systems of equations, I want you to go ahead and label them as well. Okay, for the second one, we have a y-intercept at negative 2, and then a slope of negative 4. If we write that as a fraction, that becomes negative 4 over 1. So we can go down 1, 2, 3, 4 over 1, put a point, and then continue to do the same thing in the right direction, and then to the left, go backwards. So up 1, 2, 3, 4, over to the left 1. Okay, now make sure when you do this, you're trying to fill the entire coordinate grid. not just a section of it. And then we have both of our lines plotted. So this is what we're going to talk about in a second. This, in essence, is a system of equations where you have multiple equations being graphed at the same time, or you're trying to solve for their solution, their common solution, okay? So if we were solving this system of equations, you guys may remember from previous math classes, we would be looking to see where do they overlap or where do they intersect. And again, we'll talk about that on the next slides. Okay, so what is a system of equations? I just briefly mentioned this. System means multiple things at a time, okay? So when we are talking about a system of linear equations, that means we have two or more. So at least two equations that we're looking at the same time, and all that we're going to be doing today is dealing with linear equations, so the ones that we were just looking at. Most linear equations you're going to see are going to be written in slope-intercept form, or this standard form right here, ax plus by equals c. And if you see that, we can easily convert this to slope-intercept form, which I'll show you guys how to do shortly. Okay, and like I just briefly mentioned on the previous slide, a solution to a system of equations with two variables is what we call an ordered pair, or in essence, just a point of intersection that satisfies both equations. So meaning you could plug that point in, whatever that point is, x comma y, into both equations and it would work. It would be a solution. Okay, there's some other vocab words here that I would like for you guys to make a note of. So we are going to talk about consistent versus inconsistent solutions and dependent versus independent. So if you have a system of equations that has at least one solution, so it could have one solution, two solutions, etc., three solutions, at least one though, it is what we call consistent. So it's consistent. You can always bank on the fact that it's going to have that one solution or those two solutions or those three solutions. Now, if a system of equations has no solutions, then we say it is inconsistent, okay? And the easy way to remember this is just thinking of, well, there's no consistent answer I can bank on. There's no solution. I don't have one ordered pair like we talked about on the previous slide here that satisfies both equations. So it is inconsistent if there's no solution. Okay, now dependent versus independent. So if a system of two linear equations in two variables, because we will at some point talk about systems with three variables, if it has an infinite number of solutions, then the equations are dependent. And this will make a little bit more sense when I show you guys graphs on the next slide. So for now, just make a note of this, and then I'll show you what I'm actually talking about. So that would be independent, or that would be dependent. And then if it does not have an infinite number of solutions, so in other words, if it has a finite number of solutions, meaning just one solution or two solutions or three solutions, a number you can actually count, then the system of equations is independent, okay? So here's a really good graphical representation of what I was just talking about. So in a typical system of equations where you have just one solution or one point of intersection, like this first one, you have intersecting lines, okay? They cross once, and so we can always bank on the fact that we're going to have that consistent solution every single time, like we just talked about consistency versus inconsistency. And then when it comes to independence or dependence, we basically say this is independent because we have two independent lines here. Okay, here's one in this example. Here's the other. They are independent. So if we look at our next example, whenever we have infinite solutions with a system of two equations and two variables, and we're talking about just lines here, that means they have to be the exact same line. If they have every single point in common, that means it is the same line. Okay, and so when we look again, do we have a consistent solution? Yes, we do. It's infinite solutions. They share every single solution in common, but that's consistent. We can bank on that. Now, when it comes to independent versus dependent, again, this should make some logical sense. If it's the exact same line graphed on top of itself, we don't have two independent functions. We don't have two independent lines. So this is dependent. Okay, and then in our last example here, we have parallel lines. Whenever you have parallel lines, they have the same slope. And if you have the same slope, then they are never going to intersect, which gives us no solution. Okay, so this is inconsistent because there is no solution. And when we think about the fact that we have two separate lines, they are independent of one another. This is just, like I said, a good thing for you guys to start being introduced to because this is more formal college algebra type language that you probably have not heard before in an Algebra 2 or an Algebra 1 class. Okay, so let's actually look at the steps to solving systems of equations graphically. When you're solving them graphically, you always want to start by making sure they are in slope-intercept form. So that would be step number 1. You may be given the systems, especially at this level in college algebra, in standard form like we have here. Okay, and if that's the case, then you need to rearrange to solve each equation for y and get it in y equals mx plus b form. That just tends to be the quickest and easiest way for us to graph because you can automatically identify the y-intercept and the slope. Step number 2, actually graph the equation. Step number 3, because we're solving a system, you're going to look for the point of intersection. And then step number 4, write the solution as a coordinate pair. Okay, so here is our first example. We've got our two equations here. Now notice they are not in slope-intercept form. So that's the first thing that I am going to do is to get y isolated on one side of the equation and the rest of it to look like slope-intercept form. So let me go ahead and write both of these equations here so we can do that. Okay, so for this first one, to get y by itself, I would add x to both sides. I'm going to write that out in front because, again, we want it in y equals mx plus b form, so the x term should come first. So x minus 9 divide by 3. Instead of putting this entire right side divided by 3, I'm going to divide every single term by 3. That way I can easily see the slope. Okay, so when we have x over 3, reminder that this is 1x, and so if I want to just write that as a fraction so I can see what the slope actually is, this would be 1/3 x. And then I have a minus sign, 9/3 is the same thing as 3. All right, so here's that equation. And then this next one is a little bit easier. I just have to subtract the x, so I get y equals negative x plus 1. Okay. So then we'll go ahead and graph these. So my first one, we start with a y-intercept at negative 3. The slope is 1/3. So up 1 over 1, 2, 3, put a point, up 1 over 1, 2, 3, etc. Continue the pattern, or down 1 over 3 to the left. If you ever get a V-looking graph, something has gone wrong because all of these are lines, so they should make that straight line as their shape. Okay, the next one, here's my y-intercept at positive 1. Now my slope, I just see a negative x here. Again, I have to look at, okay, how many x's do I actually have? I have negative 1x. So my slope is negative 1. If I convert that to a fraction so I can see what's the rise over run, this is negative 1 over 1. So that means I go down 1 over 1 to the right, down 1 over 1 to the right, down 1 over 1 to the right, etc. Continue the pattern, fill up the whole coordinate grid, go backwards, up 1 over 1 to the left. Okay, draw your line. Hopefully it's a little straighter than mine. Again, make sure you are labeling these lines or using different colors like I am, and then we look for a point of intersection, which is right here at positive 3, comma, negative 2. So my point of intersection is my solution, 3 comma negative 2. Okay, great. We're moving on to our second method for today, substitution method. So substitution method is one of the algebraic methods that we're going to use for solving systems of equations. We will talk about a couple of others in the next few lessons. The best time to use substitution, or the time that we use it most often, is when we already have a variable alone on one side of the equation. For instance, if you have x equals some value, let's say y plus 2, and then maybe you have a normal y equals, or let's do actually 2x minus 3y equals 4. Okay, so if you already have one of the variables isolated, like here we have x isolated, it's alone on one side of the equation, then substitution is usually going to be our quickest or easiest method. The reason that we call it substitution method, and you'll see this in a second, is because then we take what we know that value, that variable is equal to, and we can substitute it in for that same spot in the second equation, okay? So here are the steps to substitution method. So step number 1, solve either of the equations for one variable. So either solve one of the equations for y or solve one of the equations for x. Or in many cases, like we're saying, one might already be solved for you. So that's kind of nice. Then you can just skip to step 2. Step 2, then you're going to substitute the expression from step 1 that is equal to the x or the y into the other equation. Step 3, solve the resulting equation containing that one variable. So you're going to get one of your answers. You'll solve for that equation. Step 4, you're going to back substitute the value you just obtained into the other original equation to give you the other variable. Then step 5, write the solution as a coordinate point, as we talked about with graphing. And step number 6, plug both of the values for x and y, so the solution, into your original equations to check your answer. We're not always going to have you check, so just pay close attention to the directions that we give you on each problem, but this is a really easy way to go back and ensure that you've gotten the correct answer. Okay, so let's practice a couple of examples. Example number 1, we're going to see, okay, do we already have one of these equations set equal to a variable? Yes, we do. So over here, this is equal to y in my first equation. So if I know y is equal to 6x minus 11, that can be the expression that I substitute in for the y in the second equation. So I'm going to rewrite this second equation right here with my new y value. So I write negative 2x minus 3 times y, which is now becoming this expression from up above, 6x minus 11, and then that whole thing equals negative 7. Okay, and the reason that this actually works for us substitution is because now that I've substituted this value in, I have gotten rid of the y in this second equation. So I only have one variable, x, in both of these spots, and now I'm able to actually solve for x. So step number 1, we did over here. Step number 2, we substituted. Step number 3, now we solve. So I'm going to distribute this negative 3, so we get negative 2x minus 18x plus 33 equals negative 7. Continue solving, so this gives me a negative 20x plus 33 equals negative 7. I can subtract the 33 from both sides. I get negative 20x equals negative 40. Divide both sides by negative 20, and then I get x equals 2. Okay, it is very tempting or easy to kind of stop at this point and be like, oh, yay, I solved for my variable. But remember, with a system of equations, we are solving for both variables, x and y. So if we look back, this is step number 4. We are back substituting. Okay, so step number 4, I will write over here. We're going to substitute the x equals 2 into either equation. It does not matter which one. So I always just say substitute it into whichever one is going to look easiest. In this case, I would substitute it into the top equation here because I'm wanting to solve for y. So if I plug this value in for my x right here, then I can automatically get y. I don't have to isolate or, rearrange the entire equation. So y equals 6 times, plugging in that 2 instead of x, all of that minus 11, and then we get 12 minus 11, which is 1. So y equals 1. Okay, and then step number 5, we write it as a coordinate point. So 2, 1 would be our solution here. Now, if we were going to check, like I told you guys, we're not going to ask you to do this every single time, but what that means is then we have to plug this solution, 2, 1, in for both equations. So I'm going to just do that up above here. Okay, so I'm going to plug in 2 for all of my x's, and then 1 for all of my y's, and see, do they in fact satisfy both equations? So the first equation, if I plug in 1 for y here, does that in fact equal 6 times 2 minus 11? And I'm going to intentionally put a question mark over here until I confirm. Well, 6 times 2 is 12, minus 11 is in fact 1. And so yes, this does satisfy that system. Okay, then I check for the second one. So if I plug it into the second one, I have negative 2 times x, which is again 2 right here, minus 3 times y, which is 1. And I'm seeing, does that in fact equal negative 7? So I get negative 4 minus 3, and yes, that does in fact equal negative 7. And so that is my way of confirming. Okay, example number 2. So this one, same sort of process here, but the only difference now is that we do not have, like in our first example, one of the equations already set equal to y or x. On this side, I have a y plus 7. On the side, I have a negative 3x minus 2y. And so that's going to be our first step here, is to get one of these by themselves. Now, I would just pick, again, the equation that looks simplest to manipulate, or like it's going to require the least amount of work. So this one would be really simple. If I just subtract 7 from both sides, then I'm going to have y isolated. So I get 5x minus 7. Okay, so now that I've done the first step, I have my expression for y that I can then substitute in to the second equation for y. So step number 2, I go ahead and do that. So negative 3x minus 2 times y. I'm going to replace, again, y with this entire expression up here, so 5x minus 7. And then now you can see I've gotten rid of the y variable. I only have x's left, so I can go ahead and solve for x here. Same thing here. I can distribute this negative 2, and always be careful here, even if this was just like a negative 3, and I would think, okay, I can combine that with this. I technically can't because of order of operations. That tells me multiplication has to come first. So negative 3x, this becomes negative 10x plus 14. We combine our like terms. I'm going to subtract the 14 from both sides. I'll continue writing this up here. So I get negative 13x equals negative 26. Divide both sides by negative 13. And I get x equals 2. So that is our first variable. Okay, step number 4, we back substitute that into one of the original equations. Again, just pick up whichever one looks easiest. So I would probably substitute this back in for this one right here. Just because, again, y is already solved for. I've already done that work. So y equals 5 times 2, all of that minus 7. 5 times 2 gives me 10, minus 7 gives me 3. So y equals 3. And then step number 5, write your solution as a coordinate point. So x was 2, y was 3. Also, what I will caution you guys against here, make sure, even if you solve for y first, that that's going in the spot in the coordinate point for y, and that x is going in the spot for x. Because sometimes if you had these flip-flopped, let's say, and you solve for y first, y equals 2 and x equals 3, it's very easy to accidentally confuse these and write 2, 3 instead of vice versa. So just make sure you're paying attention to what actually represents each one. Okay, so now let's talk about solving systems of equations with no solution or infinite solutions, because this is where things can get a little bit trickier. So when a system does not have a solution, remember, this means the lines never intersect, so they are parallel lines. Okay, and we saw a graphical example of this. If they have the same slope, doesn't matter what the y-intercept is, as long as it's not the same y-intercept. If they have the same slope, they're going to be parallel, they're never going to intersect. Okay, what this looks like algebraically, if you're solving using substitution method, is all of your variables will cancel out typically, and you're going to be left with a statement that is not true. For example, 0 equals 5. Will 0 ever equal 5? No, it will not. And so if you end up with a non-true statement like that, what that means is that there is no solution, because no matter what you do to the left side of the equation or the right side of the equation, the left side is never going to equal the right side. 0 will never equal 5, so therefore there's no solution. Remember, we talked about earlier, no solution means it is inconsistent. Okay, and we have two different equations here, two different lines that are independent. So inconsistent and independent. All right, so let's take a look at this one. We are going to solve this algebraically, so using substitution method for now, because that's the only algebraic method we have reviewed. So I look to see, is one of the variables already solved for? Yes, y is by itself. So I'm going to take this expression for y, substitute it into the first equation here. So I rewrite x plus, instead of y, 4 minus x, and that all equals 3. And then I'm going to solve for x. So I get x plus 4 minus x equals 3. Well, what happens here is I have an x minus x, which gives me 0. So my variable cancels out or goes away, and then I'm left with 4 equals 3, which is, like we just talked about, a non-true statement. 4 is never going to equal 3. Therefore, I know that this system has no solution. And if we are writing this like an interval notation, for example, we could also write this as the null set, okay, like we talked about back in chapter R. Another way that you could really quickly kind of see this is if you were to rearrange, and you don't have to do this, but if you were to rearrange this first equation to solve for y, you would subtract x from both sides, and you would get y equals 3 minus x. And notice here, this minus x, that's the same slope for both equations. That is why there is no solution, because they both have a slope of -1, and so they would never intersect. Okay, last part of these notes, solving systems of equations with infinite solutions. So remember, we talked about when a system has the same line graphed twice, that means they coincide or they're graphed on top of each other, and so they have every single point in common, okay? What this typically looks like algebraically is that all the variables cancel out, and you're going to be left with a true statement, such as 0 equals 0. 0 always equals 0. There's never going to be a case when it doesn't. And in essence, whatever you plug into the left side of the equation is always going to equal the right side of the equation. So every single coordinate point is going to satisfy the equation. The one step that we're going to do in this class to take it a little bit further than you've done in previous classes is, instead of just stopping after we get to the point that we say, okay, there's infinite solutions, we're actually going to write our answers as a coordinate point, but either we're going to solve for y in terms of x, or we're going to solve for x in terms of y. And most often, I will tell you guys, we solve and write the answer in terms of x. So meaning we will write it as a coordinate point of x comma whatever y equals in terms of x. Okay, also quick reminder, systems that have infinite solutions, they are consistent. They always have every single point in common. We can count on that, they're consistent, but they are dependent because it is the same line that is coinciding. All right, here's a quick example. So let's go ahead and solve this one for one of our variables. Now I could do this pretty easily. Either I could get this x in the first equation by itself, or the x in the second one by itself, does not matter. So let's just say I want to get this x by itself. That means I would have to add 2y to both sides. Okay, so I'm going to get x equals 2y plus 3. And then this is what I'm going to substitute in for the x in the second equation. So 2 times, I'm going to take that x value, which is 2y plus 3 again, and set that equal to 4y plus 6. So now I distribute, I get 4y plus 6 equals 4y plus 6. Well, hopefully you guys recognize at this point that 4y plus 6 always equals 4y plus 6. But even if you don't, if you keep going and you try to get your y terms together, you're going to see very quickly, okay, those cancel out. I'm left with 6 equals 6. That's always going to be the case. Or if you subtract your 6's, 0 equals 0. That's always going to be the case. So we say, all right, we have infinite solutions. This is the same line here, coinciding. However, we're not going to stop. So now what we're going to do is write it as a coordinate point. Like I said, most times we write it in terms of x, but I will also show you how to write it in terms of y. Okay, so if we write it in terms of x, then obviously our first value is x, and then we want to write what y is, because that comes next in our coordinate point, in terms of x. So in order to do that, we have to solve one of these equations for y in terms of x. So let's go ahead and over to the side, I'm going to do that with this first equation. So x minus 2y equals 3. Okay, if I get y by itself, I would need to subtract x from both sides, and then divide everything by -2. So I'd get y equals 1/2 x minus 3/2. Okay, so then this is what I'm going to take and rewrite for my y value, 1/2 x minus 3/2. Okay, so this is my solution in terms of x. Again, this is x, this is y, or representing y, but it's in terms of x. Okay, and then last but not least, I'm just going to show you how to do this in case you want to do it in terms of y. That's totally fine as well. And what that would mean if you're doing it in terms of y is that obviously your second coordinate point is y, and your first one is x in terms of y. Well, we've already done the work for that up here. We know what x is equal to in terms of y, which is 2y plus 3. Okay, and so then that would be our solution in terms of y. So when I say in terms of y, meaning you should only see y's at the end.